All right, this is the 5.7 to 5.9 review worksheet, and as always, I am the amazing Mr. Jansen, so here we go. If I look at this first one, we just want to rewrite this using rational exponents. Remember, the cube root of something is the same thing as raising it to the 1/3 power. So this is like x to the 5th raised to the 1/3 power. And then our rules of exponents tell us to multiply, so that would be x to the 5/3. And keep in mind, the shortcut here is that the root becomes the denominator, the exponent becomes the numerator. Okay, and that's it. For the next one, it asks us to rewrite using radical symbols. And this is the reverse of what we just did. Keep in mind that this is the same thing as 7 times 1/2. And then raising something to the 1/2 power is the same thing as taking the square root. So it's the square root of x to the 7th. Okay, and if you had the little 2 in here, that's fine. That means the same thing. Typically, when we have a square root, we don't write the 2. The other acceptable answer here would be the square root of x, and then that whole thing raised to the 7th power. So again, the root is the same thing as the denominator. The exponent is the numerator. For this one, we want to solve for x, and just like with anything else, we isolate the most complicated piece first. So we're going to isolate the radical, so I have to get the radical by itself. I'm going to subtract the 6 from each side, so I'll be left with the square root of x minus 2 equals a 2. And now that the square root's by itself, I can undo it by raising each side to the 2nd power. Remember, roots and exponents cancel each other out, so here the square root and the squared cancel each other out. I'm left with an x minus 2. Over here, 2 to the 2nd power is 4, and now I can finish solving this. So I add the 2 to each side, and I find out that x equals a 6. And you can plug that back in and check it, and when you plug it back in, it works. For the next one, again, I want to isolate the radical part, so I'm going to subtract the 1 from each side. So that gives me a 2 times the square root of 2x equals 8. Now the radical's still not by itself. I still have 2 times the radical symbol, so I got to get the radical by itself. So I've got to get rid of that 2 that's being multiplied, so I divide each side by 2. That gives me the square root of 2x equals a 4. And now that the radical's by itself, now I can undo the root by raising each side to the appropriate power. So here, to undo a square root, I'm going to square each side, so I raise each side to the 2nd power. The root and the exponent cancel each other out. I'm left with a 2x. Over here, 4 to the 2nd power is going to give me a 16. And now I can finish solving this thing. I divide each side by 2, and I find out that x equals 8. And once again, if I plug that back in, I find out that it works. So always check your answers. Check for extraneous solutions. For the next one, again, I want to isolate the radical. The radical's not by itself. I want to get it by itself, so I've got to add 4 to each side. And when I do that, it leaves me with 3 times the cube root. That is an ugly looking 3 in there. Let me try again. Times the cube root. There we go. Now I can read it. Of 2x equals a positive 3. And once again, the radical's still not by itself because I'm multiplying by that 3. So I have to divide each side by 3. So when I do that, I get the cube root of 2x equals a 1. Now the radical's by itself, so now I raise each side to the appropriate power. To undo the cube root, I have to cube each side. So to undo a 3rd root, I raise each side to the 3rd power. The root and the exponent cancel each other out. I'm left with a 2x. Over here, 1 to the 3rd power is 1. And now I can finish solving this for x. I divide each side by the 2. So I find out that x equals a 1/2. And I just leave it as a fraction. So x equals 1/2, and that's it. Take a look at the next one. Whenever we have the square root of a negative, we're going to be dealing with imaginary numbers here. And this one is a perfect cube. If you want, you could think of it this way. This is the square root of -1 times 169. And now think of it as the square root of 169 being a 13. And then our exact definition, let me rewrite that, 13. Our exact definition of imaginary number is the square root of -1. So the square root of -1, I call I, the imaginary number I. So this is 13i, and that's it. For number 7, I'm just multiplying. So I multiply these things. 3i times a -2i gives me a -6i squared. So now I have -6i squared times 4i. When I multiply that, it gives me a -24i cubed. And then the real test here is just to remember that we have to simplify powers of I. If we think about our pattern, I to the first is I to the second is -1, I to the third is a negative I to the fourth is 1, and then the pattern repeats. So I to the third power is actually equal to a negative I. So this says negative 24 times I to the third, which is a negative I. And now negative 24 times a negative I is a positive 24I. So again, we have to simplify our powers of I, and that's the goal here. In number 8, we're simplifying the power of I. And remember, this pattern, the I, negative 1, negative I, 1, it repeats every fourth exponent. So I have to find the closest exponent that's divisible by 4. So again, the pattern is I, negative 1, negative I, 1. And then that repeats I, negative 1, negative I, 1. And that continues forever in each direction. So if I look at something like I to the 240th power, that's the closest exponent that's divisible by 4, that's going to equal a 1. Any exponent that's divisible by 4 is going to be equal to the 1 here. So that puts me right here in my pattern, which means I to the 243, this would be 241, 242, 243 would be at negative I. Okay, so I just have to count forward in my pattern. That's going to give me a negative I. For the next one, I do pretty much the same thing. I look for the closest exponent that's divisible by 4. And again, just look at the last two digits. I to the 1312 is divisible by 4 because the last two digits are divisible by 4. So that's going to equal a 1. So that puts me right here in the pattern. And I just have to count up 1. I to the 1313 would be right here at I. So this is going to equal an I. So again, we use our pattern I, negative 1, negative I, 1, and we count forwards or backwards from where the pattern stops and starts over again. Okay? For this next one, remember, we treat these almost like they're variables, even though I know they're imaginary numbers. So when I do this, I'm essentially just combining like terms. With this one, I can drop the parentheses because it's a plus. I can just go ahead and combine like terms. 2 plus 8 is going to give me a 10. And then the 3i and the minus 5i is going to give me a negative 2i. And that's it. We combine like terms, it leaves me with another complex number. For number 11, it's essentially the same thing, but in this one I would recommend distributing this negative sign first, just so we don't make a sign error. So we get 2 plus 3i minus 8 plus 5i. And now essentially we do the same thing. We combine like terms. That's going to give me a negative 6. The 3i and the 5i is going to give me a plus 8i. And that's it. I combine like terms. I've got my real part. I've got my imaginary part of my complex number. In number 12, again, I treat this as if it was a variable, but remember that it's not. So if I'm treating it like a variable, I distribute the 2. So that's going to give me a 16 minus 10i. And now I distribute the 3i. That's going to give me a plus 24i minus 15i squared. And now I just have to simplify this. I combine the like terms in the middle. That's going to give me a 16 plus 14i minus 15 times I squared. But remember, I squared is a negative 1. So it's just like variables, except we have to replace the powers of I because we know they're imaginary numbers. We have these equivalencies that we need to take into consideration. So negative 15 times a negative 1 is a positive 15. So it becomes a plus 15. So now this thing's going to equal, when I combine like terms, a 31 plus 14i. And that's it. In number 13, we're rationalizing the denominator. And remember, what that means with imaginary numbers is that I have to get rid of all the imaginary terms. Because an imaginary term is a radical, I'm still eliminating all the radical terms from the denominator, just like I used to do when I was talking about radicals. Here, I've got to get rid of the i's, but I approach it the same way. I have to multiply by the conjugate. So here I multiply by the conjugate. Whatever I do to the denominator, I also have to do to the numerator. And remember, I don't care if there's imaginary terms in the numerator. I got to get them out of the denominator. And now with each of these, I'm going to have to distribute or FOIL when I multiply these things. So in the numerator, I'm going to distribute the 4. That's going to give me a 12 plus 8i. Then I'm going to distribute the plus I, which is going to give me a plus 3i plus 2i squared. In the denominator, again, I distribute or FOIL, distribute the 3. That's a 9 plus 6i. And then a minus 6i minus 4i squared. And now from here, I just have to simplify everything. In the numerator, that's a 12 plus 11i plus 2 times I squared, which is a negative 1. Again, we have to replace powers of I. In the denominator, the middle terms cancel out. So I've got 9 minus 4 times I squared, which again is a negative 1. And I've got to simplify this all the way. So that's going to be a 12 plus 11i minus 2 over 9 plus 4. And that's going to give me a 10 plus 11i over 13. And from there, that's all I do because I can't simplify this any further. There's nothing that reduces here, so that's my answer. And again, I have a 13 in the denominator. There's no I values left. There's no imaginary numbers left. In this next one, there's a boatload of things that I can multiply by here in order to eliminate the radical from the denominator. I'm going to do the easiest one, which is to multiply by a negative I. And I do that because I want to turn that denominator into an I squared, but I know that I squared is negative, and I don't like negatives in the denominator. I could just multiply by I could multiply by 3i, I could multiply by negative 3i. I would just have to do more reducing. So for this one, I'm going to distribute the negative I. That's going to give me a negative 5i plus a 2i squared over a negative 3i squared. And now from here, I have to simplify this. That's a negative 5i plus 2 times a negative 1, because that's what I squared is. Negative 3 times a negative 1, because that's what I squared is. Now when I simplify this, that's going to give me a negative 5i minus 2 over a positive 3. And that's kind of why I multiplied by the negative. I wanted a positive 3 in the denominator. But now I would rewrite this as a negative 2 minus 5i over 3. So this way I have my real part followed by my imaginary part. Okay?